What if the next giant leap for humanity isn't just about reaching the moon or Mars, but about unlocking the secrets of the cosmos itself? Imagine a future where we're not just visitors to space, but pioneers, building civilizations among the stars. This isn't science fiction, it's the future we're actively shaping today. Welcome to a journey through 30 groundbreaking concepts in deep space exploration technologies. Ideas that will redefine how we understand the universe and our place within it. From harnessing the power of sunlight to propel spacecraft to the theoretical possibilities of faster-than-light travel, these innovations are not just dreams, they're the blueprints for humanity's next chapter. Stay with us because by the end of this video, you'll see the cosmos in a whole new light. And you might just find yourself inspired to imagine what's possible when we dare to reach for the stars. Let's dive in. Now, let's set our sights on the first concept that could revolutionize how we travel through space: LightSail propulsion. Picture this. Instead of relying on heavy fuel tanks or complex engines, what if we could harness the power of sunlight itself to push spacecraft forward? This isn't just a futuristic idea. It's a technology that's already being tested today. LightSail propulsion works by using large, ultra-thin reflective sails that capture the momentum of photons, the tiny particles of light emitted by the sun. When these photons hit the sail, they transfer their energy, gently pushing the spacecraft forward. It's like a cosmic wind pushing a sailboat, but instead of wind, it's sunlight. One of the biggest advantages of LightSail propulsion is its simplicity and efficiency. Unlike traditional rocket engines that require massive amounts of fuel, LightSails don't need any fuel at all. This makes them incredibly lightweight and cost-effective, perfect for long-duration missions where carrying extra fuel would be impractical. Plus, because sunlight is constant and abundant in space, a LightSail-equipped spacecraft could theoretically keep accelerating for years, reaching speeds that would be impossible with conventional propulsion methods. But what does this mean for the future of space exploration? Imagine sending probes to the farthest reaches of our solar system, or even beyond, without worrying about fuel constraints. LightSail technology could enable missions to distant asteroids, comets, or even neighboring star systems, opening up possibilities for discovery that we've only dreamed of. And while it might not be the fastest method for human travel, it's a game changer for unmanned missions where time is less of a concern than efficiency and sustainability. As we look ahead, LightSail propulsion represents a bold step toward a future where we harness the natural resources of space to explore the cosmos. It's a reminder that sometimes the most revolutionary ideas are also the simplest. And with that, let's move on to our next concept, where we'll explore how nuclear thermal rockets could take us to Mars and beyond in record time. Now, let's shift gears and explore a concept that could redefine how we think about speed in space: nuclear thermal rockets. Imagine cutting the travel time to Mars in half or even more. Sounds like science fiction, right? But with nuclear thermal propulsion, this could become a reality. Unlike traditional chemical rockets, which burn fuel to create thrust, nuclear thermal rockets use the heat generated by a nuclear reactor to superheat a propellant like hydrogen. This heated gas is then expelled at incredibly high speeds, creating thrust that's far more efficient than what chemical rockets can achieve. The key advantage here is efficiency. Nuclear thermal rockets can produce much more thrust with far less propellant compared to their chemical counterparts. This means spacecraft could carry less fuel and more payload, whether that's scientific instruments, supplies, or even habitats for future Mars colonies. And because they're so efficient, they could drastically reduce travel times. For example, a trip to Mars that currently takes around 7 months with chemical propulsion could be shortened to just 3 or 4 months with nuclear thermal rockets. That's not just a time saver, it's a game changer for astronaut safety and mission feasibility. But how does it work? At the heart of a nuclear thermal rocket is a compact nuclear reactor. This reactor heats hydrogen gas to extreme temperatures, turning it into a high-speed jet of exhaust. The process is similar to how a steam engine works, but instead of steam, it's superheated hydrogen. And because hydrogen is the lightest element, it can be accelerated to much higher speeds, making the rocket incredibly efficient. Of course, there are challenges. Handling nuclear materials in space requires rigorous safety measures, and the technology is still in its developmental stages, but the potential benefits are enormous. Not only could nuclear thermal rockets make Mars missions faster and more practical, but they could also open the door to exploring even farther destinations like the moons of Jupiter and Saturn. As we look to the future, nuclear thermal propulsion represents a bold leap forward in our quest to explore the solar system. It's a reminder that sometimes the most powerful solutions come from harnessing the energy of the atom itself. And with that, let's turn our attention to the next concept, where we'll dive into the fascinating world of ion drives and their potential to take us to the outer reaches of the solar system. Now, let's venture into the realm of ion drives, a technology that might not have the raw power of nuclear thermal rockets but offers something equally remarkable: endurance. Picture a spacecraft that can glide through the vastness of space for years, even decades, without needing to refuel. That's the promise of ion propulsion. Unlike traditional rockets that rely on explosive chemical reactions, ion drives use electricity to accelerate charged particles or ions to generate thrust. It's a slow and steady approach, but one that could take us to places we've only dreamed of reaching. So, how does it work? At its core, an ion drive uses solar panels or a nuclear power source to generate electricity. This electricity is then used to ionize a propellant, usually xenon gas, by stripping electrons from its atoms. The resulting positively charged ions are accelerated through an electric field and expelled out of the engine at incredibly high speeds, up to 10 times faster than the exhaust from chemical rockets. While the thrust produced is much smaller, the efficiency is unparalleled. Over time, this continuous, gentle push can build up to astonishing speeds, making ion drives ideal for long-duration missions. One of the most famous examples of ion propulsion in action is NASA's Dawn spacecraft, which used this technology to explore the asteroid Vesta and the dwarf planet Ceres. Dawn's ion drive allowed it to travel between these two distant worlds, something that would have been nearly impossible with conventional propulsion. This mission demonstrated the incredible potential of ion drives for exploring multiple destinations in a single trip, a capability that could revolutionize deep space exploration. But the applications don't stop there. Ion drives could be the key to reaching the outer planets and beyond. Imagine a mission to Jupiter's icy moon Europa or Saturn's enigmatic Titan, powered by an ion drive that keeps going long after chemical rockets would have run out of fuel. These missions could carry advanced scientific instruments, rovers, or even landers, all made possible by the efficiency and longevity of ion propulsion. Of course, there are challenges. Ion drives require a lot of electrical power, which means they need large solar arrays or compact nuclear reactors. They also take time to build up speed, making them less suitable for missions that require quick maneuvers. But for missions where patience and precision are key, ion drives are unmatched. As we look to the future, ion propulsion could play a crucial role in humanity's journey to the stars. It's a technology that embodies the spirit of exploration, steady, relentless, and full of potential. And with that, let's turn our attention to the next concept, where we'll explore the mind-bending possibilities of warp drive theory and what it could mean for faster-than-light travel. Now, let's shift gears and dive into one of the most fascinating and speculative concepts in deep space exploration: warp drive theory. Imagine a spacecraft that doesn't just travel through space but bends the fabric of space-time itself, allowing it to move faster than the speed of light without breaking the laws of physics. Sounds like science fiction, right? Well, it might not be as far-fetched as it seems. At the heart of warp drive theory is the idea of manipulating space-time, the four-dimensional fabric that makes up our universe. Instead of moving through space, a warp drive would contract space in front of the spacecraft and expand it behind, effectively creating a warp bubble that carries the ship along. This concept was first proposed by physicist Miguel Alcubierre in 1994, and it's often referred to as the Alcubierre drive. The Alcubierre drive relies on a phenomenon known as negative energy or exotic matter, a theoretical form of matter that has negative mass. This exotic matter would be used to create the warp bubble, bending space-time in a way that allows the spacecraft to travel faster than light relative to an outside observer, while the ship itself remains stationary within the bubble. This means the spacecraft wouldn't experience the effects of acceleration, such as time dilation, making it a potentially game-changing technology for interstellar travel. But before we get too excited, let's talk about the challenges. For one, the amount of energy required to create a warp bubble is staggering. Some estimates suggest it would take the equivalent of the mass energy of an entire star. And then there's the issue of exotic matter, which has never been observed in nature and remains purely theoretical. Even if we could find or create it, controlling it to form a stable warp bubble would be an engineering feat beyond our current capabilities. Despite these hurdles, the possibilities are tantalizing. A functioning warp drive could reduce travel times to nearby star systems from thousands of years to just a few months or even weeks. Imagine visiting Proxima Centauri, our closest stellar neighbor, or exploring the potentially habitable planets in the TRAPPIST-1 system. The implications for science, exploration, and even the search for extraterrestrial life are profound. Researchers are already exploring ways to make warp drives more feasible. Some studies suggest that modifying the shape of the warp bubble or using alternative forms of energy could reduce the energy requirements. Others are investigating whether quantum effects or advanced materials could bring us closer to realizing this dream. While we're still far from building a warp drive, the theoretical groundwork is being laid, and the pursuit of faster-than-light travel continues to inspire scientists and dreamers alike. As we ponder the possibilities of warp drives, let's turn our attention to another revolutionary concept: space elevators. These towering structures could change the way we access space, making it cheaper and more efficient than ever before. But how do they work, and what challenges stand in the way of making them a reality? Let's find out. Now, let's take a step back from the realm of theoretical physics and explore a concept that feels a bit more grounded literally. Space elevators are one of the most ambitious ideas in space exploration, offering a radical new way to reach orbit without the need for traditional rockets. Picture this: a towering structure stretching from the Earth's surface all the way into space, acting like a cosmic elevator that transports people and cargo effortlessly. It's a concept that could completely transform how we access space, making it cheaper, safer, and more sustainable. At its core, a space elevator consists of three main components: a tether, an anchor, and a counterweight. The tether is a long, incredibly strong cable that extends from the Earth's surface to a point in space, typically geostationary orbit, which is about 35,000 kilometers above the equator. The anchor is a massive structure on the ground that holds the tether in place, while the counterweight, located at the far end of the tether, keeps the entire system stable by balancing the forces acting on it. Climbers or robotic vehicles would travel up and down the tether, carrying payloads into orbit. The key challenge in building a space elevator lies in the tether material. It needs to be incredibly strong yet lightweight, capable of withstanding the immense tension and stress caused by gravity, wind, and other forces. Traditional materials like steel or aluminum simply aren't up to the task. Enter carbon nanotubes, a revolutionary material that's stronger than steel but much lighter. while carbon nanotubes show promise, producing them in the lengths and quantities needed for a space elevator remains a significant hurdle. Researchers are also exploring other advanced materials, such as graphene and boron nitride nanotubes, which could offer similar strength-to-weight ratios. So, why go through all this trouble? The benefits of a space elevator are enormous. First, it would drastically reduce the cost of sending payloads into space. Traditional rockets are expensive because they require massive amounts of fuel and are single-use or partially reusable. A space elevator, on the other hand, would operate more like a train or a conveyor belt, making space travel more affordable and accessible. Second, it would be far safer, eliminating the risks associated with rocket launches, such as explosions or mechanical failures. And third, it would enable more frequent and sustainable access to space, paving the way for large-scale projects like space-based solar power, asteroid mining, and even space tourism. But let's not overlook the challenges. Beyond the material requirements, there are significant engineering and logistical hurdles. The tether would need to be protected from space debris, micrometeoroids, and even weather conditions like lightning strikes. Maintaining the stability of such a massive structure would also require precise control systems and constant monitoring. And then there's the question of international cooperation. Building a space elevator would likely require collaboration between nations, as well as agreements on how to manage and regulate this new form of space access. Despite these challenges, the potential of space elevators is too great to ignore. Imagine a future where launching satellites, building space stations, or even sending humans to Mars becomes as routine as boarding a plane. It's a vision that could redefine our relationship with space, making it an integral part of our daily lives rather than a distant frontier. As we marvel at the possibilities of space elevators, let's turn our attention to another groundbreaking concept: orbital habitats. These futuristic structures could serve as homes for humans in space, enabling long-term exploration and even colonization of other worlds. But what would it take to build them, and how could they support life in the harsh environment of space? Let's find out. Now, shifting our gaze from the towering ambition of space elevators, let's venture into the realm of orbital habitat structures designed to house humans in the vast expanse of space. These habitats are not just futuristic concepts, they are essential stepping stones for humanity's journey into deep space. Imagine floating cities orbiting Earth or other planets, providing a safe haven for astronauts, scientists, and even future space colonists. These habitats could serve as research hubs, manufacturing centers, and even tourist destinations, making space a place where humans can live and thrive for extended periods. At the heart of orbital habitats is their design. Unlike the cramped quarters of the International Space Station, these habitats would be spacious, modular, and self-sustaining. Picture a series of interconnected modules, each serving a specific purpose: living quarters, laboratories, greenhouses, and recreational areas. The design would prioritize comfort and functionality, ensuring that inhabitants can live and work efficiently while minimizing the psychological challenges of long-term space habitation. Artificial gravity generated through rotation could be a key feature, helping to counteract the negative effects of prolonged weightlessness on the human body, such as muscle atrophy and bone density loss. But how would these habitats support life in the harsh environment of space? The answer lies in advanced life support systems. These systems would recycle air, water, and waste, creating a closed-loop ecosystem that mimics Earth's natural cycles. For example, plants grown in onboard greenhouses could produce oxygen and food while absorbing carbon dioxide. Water would be purified and reused, reducing the need for constant resupply missions from Earth. Additionally, radiation shielding would be critical to protect inhabitants from harmful cosmic rays, which pose a significant risk to human health during long-duration missions. Orbital habitats also play a pivotal role in deep space exploration. They could serve as way stations for missions to the Moon, Mars, and beyond, providing a place to refuel, repair equipment, and rest before continuing the journey. For instance, a habitat orbiting the Moon could act as a staging point for lunar exploration, while one near Mars could support missions to the Red Planet. These habitats could also serve as testing grounds for technologies needed for interplanetary travel, such as advanced propulsion systems and resource extraction techniques. The potential applications of orbital habitats extend beyond exploration. They could revolutionize industries like manufacturing and tourism. In the microgravity environment of space, materials can be produced with unique properties that are impossible to achieve on Earth. Think of ultra-pure crystals for electronics or lightweight alloys for aerospace engineering. Meanwhile, space tourism could become a reality, with orbital habitats offering breathtaking views of Earth and the cosmos, creating a new frontier for adventure and discovery. However, building and maintaining these habitats is no small feat. The challenges are immense, from the high costs of construction and transportation to the technical difficulties of creating self-sustaining ecosystems. International collaboration will be crucial, as no single nation or organization can tackle these challenges alone. Moreover, ethical considerations must be addressed, such as the equitable use of space resources and the potential impact on Earth's environment. Despite these hurdles, the vision of orbital habitats is a compelling one. They represent a future where humanity is no longer confined to Earth but can live and work among the stars. As we continue to push the boundaries of space exploration, these habitats could become the foundation of a new era, one where space is not just a destination but a home. With the possibilities of orbital habitats in mind, let's now turn our attention to another critical technology for long-duration space missions: artificial gravity. How can we simulate gravity in space, and what role does it play in ensuring the health and well-being of astronauts? Let's explore this next. Now, as we transition from the concept of orbital habitats, let's dive into a technology that could redefine how humans experience life in space: artificial gravity. Imagine floating effortlessly in zero gravity. It might sound fun at first, but prolonged exposure to weightlessness can take a serious toll on the human body. Muscle atrophy, bone density loss, and even changes in vision are just some of the challenges astronauts face during long-duration missions. This is where artificial gravity comes in, offering a solution to keep astronauts healthy and functional as they venture deeper into space. So, how does artificial gravity work? The most straightforward method involves rotation. Picture a spacecraft or habitat spinning like a merry-go-round. The centrifugal force generated by this rotation would push objects outward, creating a sensation similar to gravity. This concept, often seen in science fiction, is grounded in real physics. By carefully designing the size and speed of the rotating structure, we could simulate gravity levels comparable to those on Earth, Mars, or even the Moon, depending on the mission's needs. But creating artificial gravity isn't as simple as spinning a spacecraft. The design must balance rotation speed and radius to avoid causing discomfort or disorientation. For example, a smaller rotating structure would need to spin faster to generate the same gravitational effect, which could lead to motion sickness or dizziness. On the other hand, a larger structure would require slower rotation, making it more comfortable but also more challenging to build and launch into space. This is why researchers are exploring modular designs and innovative materials to make rotating habitats both practical and efficient. Artificial gravity isn't just about comfort, it's a necessity for long-term space exploration. Without it, astronauts on missions to Mars or beyond could face severe health risks, jeopardizing the success of their missions. By simulating gravity, we can mitigate these risks, ensuring that astronauts remain physically and mentally fit throughout their journeys. This technology could also play a crucial role in future space settlements, where humans might live and work for years or even generations. beyond health benefits, artificial gravity opens up new possibilities for space research and industry. In a gravity-controlled environment, scientists could conduct experiments that are impossible in zero gravity, such as studying the effects of partial gravity on plant growth or human physiology. Industries like manufacturing could also benefit as gravity influences processes like fluid dynamics and material crystallization. Imagine producing advanced materials or pharmaceuticals in space, tailored to specific gravitational conditions. Of course, developing artificial gravity systems comes with its own set of challenges. The engineering complexity, energy requirements, and cost of building rotating habitats are significant hurdles. Additionally, we need to ensure that these systems are reliable and safe, especially for long-duration missions where equipment failure could have dire consequences. International collaboration and advancements in materials science, robotics, and propulsion will be key to overcoming these obstacles. As we look to the future, artificial gravity could become a cornerstone of deep space exploration. It's not just about making space travel more comfortable, it's about enabling humanity to thrive beyond Earth. With this technology, we can take the next giant leap, ensuring that astronauts and future space colonists can live, work, and explore in environments that feel a little more like home. With the potential of artificial gravity in mind, let's now turn our attention to another groundbreaking concept: self-replicating robots. How can machines that build themselves transform the way we explore and settle the cosmos? Let's explore this next. Now, shifting our focus to a concept that sounds like it's straight out of a science fiction novel, let's explore the fascinating world of self-replicating robots. Imagine machines that can build copies of themselves, using materials found in space to create an entire workforce without human intervention. This idea, once purely theoretical, is now being seriously considered as a game-changer for deep space exploration and colonization. So, how do self-replicating robots work? At their core, these robots are designed to perform two critical tasks: manufacturing and assembly. Using advanced artificial intelligence and robotics, they can identify raw materials such as metals and minerals from asteroids or the moon and process them into usable components. These components are then assembled into new robots, effectively creating a self-sustaining system. The key here is autonomy. These robots must be able to operate independently, making decisions and solving problems without constant human oversight. The potential applications of self-replicating robots in space are immense. One of the most significant roles they could play is in building infrastructure. Before humans arrive at a distant planet or moon, these robots could be sent ahead to construct habitats, landing pads, and even energy systems. By the time astronauts arrive, they'd find a fully functional base ready to support their mission. This not only reduces the risks for human explorers, but also cuts down on the cost and complexity of transporting heavy equipment from Earth. Another exciting possibility is resource utilization. Self-replicating robots could mine asteroids or other celestial bodies for valuable materials, such as water, metals, and rare minerals. These resources could then be used to fuel further exploration or even sent back to Earth. This concept, known as in situ resource utilization, could revolutionize how we approach space missions, making them more sustainable and cost-effective. But the benefits don't stop there. These robots could also support human missions by maintaining and repairing equipment, ensuring that critical systems remain operational during long-duration missions. Imagine a scenario where a spacecraft's solar panels are damaged by micrometeoroids. Instead of risking human lives to conduct repairs, self-replicating robots could be deployed to fix the issue quickly and efficiently. Of course, developing self-replicating robots is no small feat. The technology required is incredibly complex, involving advancements in robotics, artificial intelligence, and materials science. One of the biggest challenges is ensuring that these robots can operate reliably in the harsh conditions of space, where radiation, extreme temperatures, and limited resources pose significant obstacles. Additionally, there are ethical and safety concerns to consider. What happens if a self-replicating robot malfunctions or begins replicating uncontrollably? These are questions that researchers are actively working to address. Despite these challenges, the potential of self-replicating robots is too great to ignore. They could fundamentally change how we explore and settle the cosmos, enabling missions that were once thought impossible. By taking on the heavy lifting literally, these robots could pave the way for humanity's expansion into the stars. As we look ahead, the idea of self-replicating robots opens up a world of possibilities. From building colonies on Mars to mining asteroids for resources, these machines could become indispensable partners in our journey through the cosmos. With this in mind, let's turn our attention to another revolutionary concept: asteroid mining. How can we harness the riches of space to fuel our exploration efforts? Let's dive in next. Now, let's venture into the realm of asteroid mining, a concept that could unlock the vast riches of space and propel humanity's exploration efforts to new heights. Imagine a future where we no longer rely solely on Earth's dwindling resources, but instead tap into the abundance of materials floating in the asteroid belt. This idea, once the stuff of dreams, is now being actively pursued by scientists and engineers as a viable way to sustain and expand our presence in space. Asteroid mining revolves around the extraction of valuable resources from asteroids, which are essentially rocky remnants left over from the formation of our solar system. These celestial bodies are rich in metals like iron, nickel, and platinum, as well as rare minerals and even water. Water, in particular, is a game changer. It can be split into hydrogen and oxygen to create rocket fuel, providing a crucial resource for refueling spacecraft during long missions. This concept, known as in situ resource utilization, could drastically reduce the cost and complexity of deep space exploration by allowing us to live off the land in space. So, how do we mine asteroids? The process begins with identifying suitable targets. Not all asteroids are created equal. Some are metallic, while others are carbon-rich or icy. Space agencies and private companies are already developing advanced telescopes and probes to locate and analyze these targets from afar. Once a promising asteroid is identified, the next step is to send a mining spacecraft equipped with specialized tools. These tools could include drills, robotic arms, and even systems to heat the asteroid's surface and extract water or metals. One of the most exciting aspects of asteroid mining is its potential to revolutionize space travel. By harvesting resources in space, we could build and refuel spacecraft without the need to launch everything from Earth. This would significantly reduce the cost of missions and enable longer, more ambitious journeys. For example, a mining operation on a water-rich asteroid could produce fuel for a mission to Mars, making the red planet more accessible than ever before. But the benefits don't stop at fuel production. The metals and minerals extracted from asteroids could also be used to construct habitats, spacecraft, and other infrastructure in space. Imagine a future where entire space stations or colonies are built using materials mined from asteroids, eliminating the need to transport heavy payloads from Earth. This would not only save money but also open up new possibilities for sustainable living in space. Of course, asteroid mining is not without its challenges. The technology required is still in its early stages, and the logistics of operating in the harsh environment of space are daunting. Asteroids are often far from Earth, and their low gravity makes it difficult to anchor mining equipment. Additionally, there are legal and ethical questions to consider. Who owns the resources extracted from asteroids? How do we ensure that mining operations are conducted responsibly and sustainably? These are complex issues that will require international cooperation and careful regulation. Despite these hurdles, the potential rewards of asteroid mining are too significant to ignore. It could provide the resources needed to fuel humanity's expansion into the solar system, from establishing colonies on the Moon and Mars to exploring the outer reaches of our cosmic neighborhood. By turning asteroids into stepping stones, we could unlock a new era of space exploration. With this in mind, let's turn our attention to another groundbreaking concept: interstellar probes. How can we send unmanned missions to nearby star systems, and what might they discover? Let's explore this next frontier together. Now, let's shift our gaze beyond our solar system and into the vast expanse of interstellar space, where the concept of interstellar probes opens up a realm of possibilities. Imagine sending unmanned spacecraft to explore nearby star systems, uncovering secrets of distant worlds and potentially answering one of humanity's most profound questions: are we alone in the universe? This ambitious idea, while still in its infancy, represents the next logical step in our quest to understand the cosmos. Interstellar probes are designed to travel to other star systems, far beyond the reach of our current technology. Unlike missions within our solar system, which can take years, interstellar travel requires spacecraft to cover distances measured in light years. To put this into perspective, the nearest star system, Alpha Centauri, is approximately 4.3 light-years away. That means even at the speed of light, it would take over 4 years to reach it. With our current propulsion systems, such a journey would take tens of thousands of years. So, how do we bridge this immense gap? One promising solution is the development of advanced propulsion technologies. Concepts like LightSails, which use the pressure of sunlight to propel spacecraft, or laser propulsion, where powerful ground-based lasers push a spacecraft to incredible speeds, are being explored. These methods could potentially accelerate probes to a significant fraction of the speed of light, reducing travel time to nearby stars to just a few decades. For example, the Breakthrough Starshot initiative aims to send tiny, lightweight probes to Alpha Centauri within 20 years, using a powerful laser array to propel them. But speed isn't the only challenge. Interstellar probes must also be equipped to survive the harsh conditions of deep space. Cosmic radiation, extreme temperatures, and micrometeoroid impacts pose significant risks. To address these issues, engineers are developing robust shielding, advanced power systems, and autonomous navigation technologies. These probes will need to operate independently, making decisions without human intervention, as communication delays over such vast distances would make real-time control impossible. The scientific potential of interstellar probes is immense. They could provide detailed data on exoplanets, including their atmospheres, surface conditions, and potential for habitability. Imagine discovering a planet with signs of liquid water or even biosignatures, chemical markers that could indicate the presence of life. Such a discovery would revolutionize our understanding of biology and our place in the universe. Additionally, interstellar probes could study the interstellar medium, the sparse gas and dust that fill the space between stars, shedding light on the processes that shape galaxies and star systems. Of course, the challenges are as vast as the distances involved. Building and launching an interstellar probe requires overcoming significant technical, financial, and logistical hurdles. The cost of such a mission would be astronomical, and international collaboration would be essential to pool resources and expertise. There are also ethical considerations, such as the potential impact of human-made objects on alien ecosystems, should they exist. These questions will need careful consideration as we move forward. Despite these challenges, the dream of sending probes to other star systems is a powerful motivator. It represents humanity's innate curiosity and desire to explore the unknown. By pushing the boundaries of what's possible, we could unlock new scientific discoveries and inspire future generations to reach for the stars. With this in mind, let's turn our attention to another fascinating concept: cryogenic sleep. How could this technology enable long-duration space travel, and what are the ethical implications? Let's dive into this next frontier together. Now, let's venture into a concept that sounds like it's straight out of science fiction but could one day become a reality: cryogenic sleep. Imagine putting astronauts into a state of suspended animation, slowing down their biological processes to allow them to endure the long, grueling journeys to distant star systems. This idea, often depicted in movies and books, is rooted in real scientific principles and could revolutionize how we approach deep space exploration. Cryogenic sleep, or cryosleep, involves cooling the human body to extremely low temperatures, effectively putting it into a state of hibernation. At these temperatures, metabolic activity slows down dramatically, reducing the need for food, water, and oxygen. This could be a game-changer for long-duration missions where resources are limited and the psychological toll of isolation and confinement can be overwhelming. By placing astronauts in cryosleep, we could minimize these challenges, allowing them to skip the years or even decades it would take to reach their destination. The science behind cryogenic sleep is still in its early stages, but researchers are making progress. One approach involves using cryoprotectants, special chemicals that prevent ice crystals from forming in cells during the cooling process. Ice crystals can damage tissues, so finding ways to safely freeze and thaw biological material is crucial. Experiments on small animals and isolated tissues have shown promise, but scaling this up to humans presents significant hurdles. For instance, safely reviving a human from cryosleep without causing harm remains a major challenge. Beyond the technical challenges, cryogenic sleep raises important ethical questions. Who decides which astronauts undergo cryosleep and under what conditions? What happens if something goes wrong during the journey and the crew cannot be revived? There are also concerns about the long-term effects of cryosleep on the human body and mind. Would astronauts wake up disoriented or suffer from psychological trauma after years of suspended animation? These are questions that scientists, ethicists, and policymakers will need to address as this technology develops. Despite these challenges, the potential benefits of cryogenic sleep are hard to ignore. It could make interstellar travel feasible, enabling missions to distant star systems that would otherwise be impossible. It could also reduce the physical and mental strain on astronauts, making long-duration space travel more sustainable. And let's not forget the cultural impact. Cryosleep could inspire a new generation of explorers, eager to push the boundaries of human achievement. As we continue to explore the possibilities of cryogenic sleep, it's clear that this technology could play a pivotal role in humanity's journey to the stars. But it's not the only groundbreaking concept on the horizon. Next, we'll turn our attention to another innovative idea: space-based solar power. How could harvesting energy in space transform our approach to deep space missions and even life on Earth? Let's find out. Now, let's shift our focus to a concept that could redefine how we harness energy, not just for space exploration but for life on Earth as well: space-based solar power. Imagine capturing the sun's energy directly in space, where sunlight is uninterrupted by clouds, atmosphere, or the cycle of day and night. This idea, once confined to the realm of science fiction, is now being seriously explored as a potential solution to our growing energy needs and a game-changer for deep space missions. Space-based solar power involves deploying massive solar arrays in orbit around Earth or other celestial bodies. These arrays would collect sunlight continuously, converting it into electricity. But here's the fascinating part. Instead of storing this energy in batteries, it will be transmitted back to Earth or to spacecraft using wireless technologies like microwaves or lasers. This means we could have a constant, reliable source of energy, even in the farthest reaches of space. One of the biggest advantages of space-based solar power is its efficiency. On Earth, solar panels are limited by weather conditions, the angle of sunlight, and the fact that the sun isn't always shining. In space, however, solar arrays can operate at full capacity 24 hours a day, 7 days a week. This could provide a steady stream of energy for deep space missions, powering everything from life support systems to propulsion engines without the need for heavy fuel reserves. But the benefits don't stop there. Space-based solar power could also revolutionize energy production on Earth. By beaming clean, renewable energy from space, we could reduce our reliance on fossil fuels and help combat climate change. Imagine a future where entire cities are powered by energy harvested from the sun, transmitted wirelessly from satellites in orbit. It's a vision that could transform not just space exploration, but life on our planet as well. Of course, there are significant challenges to overcome. Building and launching massive solar arrays into space would require advanced materials and engineering. Transmitting energy wirelessly over such vast distances also poses technical hurdles, as we'd need to ensure the process is safe, efficient, and doesn't interfere with other systems. And let's not forget the cost. Developing and deploying space-based solar power infrastructure would require substantial investment and international collaboration. Despite these challenges, the potential of space-based solar power is immense. It could provide a sustainable energy source for long-duration missions to Mars and beyond, reducing the need for resupply missions and making deep space exploration more feasible. It could also pave the way for a cleaner, greener future here on Earth. As we continue to explore this concept, it's clear that space-based solar power could be a cornerstone of humanity's journey into the cosmos. With this innovative idea in mind, let's turn our attention to another groundbreaking technology, quantum communication. How could this cutting-edge concept enable secure, instantaneous communication across the vast distances of space? Let's dive in and find out. Now, let's venture into the realm of quantum communication, a concept that sounds like it's straight out of a sci-fi novel but is rapidly becoming a reality. Imagine a future where messages can be sent across the vast expanse of space instantly and with absolute security. This isn't just about faster communication, it's about redefining how we connect across the cosmos. Quantum communication relies on the principles of quantum mechanics, a branch of physics that deals with the behavior of particles at the smallest scales. At its core is the idea of quantum entanglement, a phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This means that if we can harness this connection, we could create a communication system that's not only instantaneous but also immune to interception or hacking. One of the most exciting applications of quantum communication is in deep space exploration. Traditional communication methods like radio waves have limitations. The farther a spacecraft travels from Earth, the longer it takes for signals to travel back and forth. For example, a message sent from Mars to Earth can take anywhere from 4 to 24 minutes, depending on the distance between the two planets. This delay makes real-time communication impossible and poses challenges for mission control. But with quantum communication, we could send and receive data instantly, enabling real-time decision-making and control, even for missions to the outer reaches of our solar system. Another game-changing aspect of quantum communication is its security. In traditional systems, encrypted messages can theoretically be intercepted and decoded given enough time and computing power. Quantum communication, however, uses quantum key distribution, a method that makes it impossible for an eavesdropper to intercept the message without altering its state. This means that any attempt to hack the communication would be immediately detected, ensuring that the data remains secure. For deep space missions, where sensitive information like navigation data or scientific findings is transmitted, this level of security is invaluable. Of course, there are challenges to overcome. Quantum communication requires highly specialized equipment, including quantum repeaters to maintain the integrity of the signal over long distances. The technology is still in its early stages, and scaling it up for practical use in space will require significant advancements. but the potential is undeniable. Quantum communication could revolutionize not just space exploration, but also fields like cybersecurity, finance, and global communication networks. As we look to the stars, the ability to communicate instantly and securely could be the key to unlocking the next chapter of human exploration. From enabling real-time collaboration between astronauts and mission control to ensuring the safety of sensitive data, quantum communication has the potential to transform how we connect across the universe. And with that, let's turn our attention to another visionary concept, terraforming. How might we transform barren planets into habitable worlds? Let's explore that next. Now, shifting our gaze to a concept that feels like the ultimate dream of science fiction turned reality, let's dive into the fascinating world of terraforming. Imagine transforming a barren, lifeless planet into a thriving, Earth-like world capable of supporting human life. It's a bold vision, but one that could redefine humanity's future in the cosmos. Terraforming, at its core, is the process of altering a planet's environment to make it habitable for humans. This could involve changing its atmosphere, temperature, and even its surface conditions to mimic those of Earth. The idea isn't just about survival, it's about creating a second home for humanity, a place where we can thrive beyond the confines of our own planet. One of the most talked about candidates for terraforming is Mars. The red planet has long captured our imagination, and with good reason. Its relatively close proximity to Earth and its similarities in day length and seasonal changes make it a prime candidate. But how exactly would we go about transforming Mars? The process would likely begin with warming the planet, as Mars is currently too cold to support liquid water, a key ingredient for life. One proposed method involves releasing greenhouse gases like carbon dioxide into the Martian atmosphere to trap heat and gradually raise temperatures. Over time, this could lead to the melting of polar ice caps, releasing water and further thickening the atmosphere. Another critical step would be creating a breathable atmosphere. Mars's current atmosphere is mostly carbon dioxide with only trace amounts of oxygen. To make it habitable, we'd need to introduce oxygen-producing organisms, such as genetically engineered algae or plants, to convert carbon dioxide into oxygen. This process, known as biological terraforming, could take centuries, but it's a crucial step toward making Mars a livable world. Of course, terraforming isn't without its challenges. The technologies required are still in their infancy, and the scale of such an endeavor is staggering. We'd need advanced robotics, massive infrastructure projects, and a deep understanding of planetary science to even begin. And then there are the ethical and environmental considerations. Should we alter an entire planet's ecosystem, even if it's currently uninhabited? What if there's microbial life on Mars that we haven't discovered yet? These questions highlight the complex moral dilemmas that come with terraforming. Beyond Mars, other celestial bodies like Venus or even some of Jupiter's moons have been proposed as potential candidates for terraforming. Each presents its own unique set of challenges and opportunities. Venus, for example, has a thick, toxic atmosphere and surface temperatures hot enough to melt lead. Transforming it would require drastically cooling the planet and removing its dense carbon dioxide atmosphere, a monumental task, but not impossible with future technologies. As we ponder the possibilities of terraforming, it's clear that this concept is about more than just survival. It's about expanding the boundaries of human potential and redefining our place in the universe. The journey to terraform another world will be long, difficult, and filled with unknowns, but the rewards could be nothing short of transformative. And with that, let's turn our attention to another groundbreaking idea: 3D printing in space. How might this technology revolutionize the way we build and explore beyond Earth? Let's find out. Now, let's take a leap into the future of manufacturing beyond Earth with the incredible potential of 3D printing in space. Imagine a world where astronauts no longer need to carry every tool, spare part, or piece of equipment with them on their missions. Instead, they could simply print what they need right there in orbit or on another planet. This isn't science fiction, it's a rapidly advancing technology that could revolutionize how we explore and live in space. 3D printing, also known as additive manufacturing, works by building objects layer by layer from materials like plastic, metal, or even specialized composites. On Earth, this technology has already transformed industries from healthcare to automotive manufacturing, but in space, its applications could be truly game-changing. One of the biggest challenges of space exploration is the sheer cost and difficulty of transporting materials from Earth. Every kilogram of cargo adds to the mission's expense, and there's always the risk of forgetting or breaking something critical. 3D printing solves this problem by enabling on-demand production, reducing the need for bulky cargo, and giving astronauts the ability to create tools and parts as needed. For example, if a spacecraft component breaks during a mission, instead of waiting months for a replacement to be sent from Earth, astronauts could print a new part in a matter of hours. This capability has already been tested on the International Space Station, where 3D printers have successfully created tools and spare parts in microgravity. These early experiments have proven that 3D printing works in space, paving the way for more ambitious applications, but the potential doesn't stop at tools and spare parts. 3D printing could also be used to construct entire habitats on the Moon or Mars. Instead of shipping prefabricated structures from Earth, which would be incredibly expensive and logistically challenging, we could send lightweight raw materials and use 3D printers to build habitats on site. These structures could be designed to withstand the harsh conditions of space, using local materials like lunar or Martian soil to create durable, radiation-resistant shelters. This approach not only reduces costs but also makes long-term colonization more feasible. Another exciting possibility is the use of 3D printing to manufacture spacecraft components in orbit. Imagine building satellites or even entire spacecraft in space, free from the constraints of Earth's gravity. This could lead to lighter, more efficient designs that are impossible to create on Earth. Additionally, in-space manufacturing could enable the repair and upgrading of satellites, extending their lifespans and reducing space debris. Of course, there are challenges to overcome. 3D printing in space requires advanced materials that can withstand extreme temperatures and radiation. The printers themselves must be reliable and capable of operating in microgravity. And we'll need to develop new techniques for using local resources, like turning lunar dust into printable material. But with ongoing research and innovation, these hurdles are steadily being addressed. The implications of 3D printing in space are profound. It's not just about convenience, it's about enabling sustainable, long-term exploration and habitation beyond Earth. By reducing our reliance on Earth-based supply chains, we can make space missions more efficient, cost-effective, and resilient. And as we look to the future, this technology could play a key role in building the infrastructure needed for human settlements on the Moon, Mars, and beyond. With that in mind, let's turn our attention to another critical technology for deep space exploration: magnetic shields. How might these protect astronauts from the dangers of cosmic radiation? Let's explore that next. Now, let's shift our focus to a technology that could be a game-changer for the safety of astronauts on long-duration missions: magnetic shields. As we venture deeper into space, one of the most significant challenges we face is protecting astronauts from the harmful effects of cosmic radiation. Unlike on Earth, where our atmosphere and magnetic field shield us from most of this radiation, space offers no such protection. Prolonged exposure to cosmic rays can lead to serious health risks, including cancer, damage to the central nervous system, and even acute radiation sickness. This is where magnetic shields come into play. Magnetic shields work by creating a protective barrier around a spacecraft or habitat, deflecting charged particles away from astronauts. The concept is inspired by Earth's own magnetic field, which naturally deflects solar and cosmic radiation. Scientists are exploring ways to replicate this effect on a smaller scale using superconducting magnets. These magnets generate a powerful magnetic field that can redirect harmful particles, effectively creating a safe zone for astronauts. One of the most promising approaches involves using toroidal or donut-shaped magnetic fields. These fields are generated by superconducting coils, which can produce a strong, stable magnetic field without requiring excessive energy. Early experiments have shown that this technology could reduce radiation exposure by up to 90%, making it a viable solution for long-term missions to Mars or beyond. However, there are still challenges to overcome, such as the size and weight of the equipment, as well as the energy required to maintain the magnetic field over extended periods. Another innovative idea is the use of active shielding systems, which combine magnetic fields with electrostatic fields to create a more comprehensive defense against radiation. These systems could be tailored to block specific types of particles, offering even greater protection. While still in the experimental phase, active shielding holds immense potential for future deep space missions. The development of magnetic shields isn't just about protecting astronauts, it's also about enabling sustainable exploration. Without effective radiation shielding, long-duration missions would be too risky to attempt. By solving this problem, we open the door to extended stays on the Moon, Mars, and even interstellar travel. It's a critical step toward making humanity a multi-planetary species. As we continue to push the boundaries of space exploration, technologies like magnetic shields will play a vital role in ensuring the safety and success of our missions. Next, let's explore another essential piece of the deep space puzzle: space tugs, and how they could revolutionize the way we transport cargo and spacecraft in orbit. Now, let's turn our attention to a concept that could transform how we move things around in space: space tugs. Imagine trying to move a heavy piece of furniture across a room without wheels. It's slow, inefficient, and exhausting. In space, moving cargo or spacecraft between orbits can feel just as cumbersome without the right tools. That's where space tugs come in. These specialized vehicles are designed to transport cargo, satellites, or even entire spacecraft from one orbit to another, making space logistics far more efficient and cost-effective. Space tugs operate by using propulsion systems to maneuver objects in space. Unlike traditional rockets, which are built for one-time launches, space tugs are reusable and can perform multiple missions. This reusability is a game changer, as it reduces the need for launching new rockets every time we need to move something in orbit. Think of them as the tow trucks of space, capable of repositioning satellites, delivering supplies to space stations, or even assembling large structures in orbit piece by piece. One of the most exciting applications of space tugs is their potential to support deep space exploration. For example, if we're planning a mission to Mars, we could use space tugs to transport fuel, habitats, or other supplies to a staging point in orbit around Earth or the Moon. This would allow us to assemble and prepare the mission components in space, rather than launching everything from Earth in one go. By breaking the mission into smaller, more manageable steps, space tugs could make deep space missions more feasible and affordable. Another key advantage of space tugs is their ability to clean up space debris. As more satellites and spacecraft are launched, Earth's orbit is becoming increasingly cluttered with defunct objects. Space tugs could be equipped with robotic arms or nets to capture and remove this debris, helping to keep our orbital highways clear and safe for future missions. This dual role, supporting exploration while maintaining a clean space environment, makes space tugs an indispensable tool for the future of space travel. Of course, there are challenges to overcome. Space tugs require advanced propulsion systems to operate efficiently, and they need to be designed to handle a wide variety of payloads. Additionally, coordinating their movements in the vastness of space requires precise navigation and communication systems. But as technology continues to advance, these hurdles are becoming more manageable, bringing us closer to a future where space tugs are a common sight in our orbital infrastructure. As we look ahead, it's clear that space tugs will play a crucial role in shaping the future of space exploration. By making it easier to move cargo and spacecraft between orbits, they'll help us build the infrastructure we need to explore deeper into the cosmos. Next, let's dive into another groundbreaking concept, laser propulsion, and how it could propel spacecraft to incredible speeds, opening up new possibilities for interstellar travel. Now, shifting our focus to a concept that sounds like it's straight out of science fiction, let's talk about laser propulsion. Imagine a spacecraft being pushed forward not by traditional rockets but by beams of light. This isn't just a futuristic dream, it's a real technology being developed that could revolutionize how we launch and propel spacecraft, potentially reaching speeds far beyond what's possible with current methods. Laser propulsion works by using powerful lasers to push a spacecraft forward. Here's how it works. A ground-based or space-based laser system directs a concentrated beam of light at a spacecraft equipped with a special reflective sail. The energy from the laser beam pushes against the sail, creating thrust. Unlike chemical rockets which burn fuel to generate propulsion, laser propulsion relies entirely on the energy of light, making it incredibly efficient and capable of achieving much higher speeds over time. One of the most exciting aspects of laser propulsion is its potential to drastically reduce the cost of launching spacecraft. Traditional rockets require massive amounts of fuel, which adds weight and expense to every mission. With laser propulsion, the energy source, the laser remains on the ground or in orbit, meaning the spacecraft itself doesn't need to carry heavy fuel. This could make space travel more affordable and accessible, opening up new opportunities for exploration and even commercial ventures, but the real game changer is the speed. Laser propulsion could accelerate spacecraft to a fraction of the speed of light, making interstellar travel a realistic possibility. For example, a mission to Proxima Centauri, the closest star system to Earth, could take just a few decades instead of thousands of years with current technology. This would allow us to send probes to nearby star systems within a human lifetime, potentially discovering habitable planets or even signs of extraterrestrial life. Of course, there are challenges to overcome. Building a laser powerful enough to propel a spacecraft over such vast distances is no small feat. The laser system would need to be incredibly precise, maintaining a steady beam on the spacecraft's sail even as it travels millions of miles away. Additionally, the spacecraft's sail would need to be made of ultra-lightweight, highly reflective materials to maximize the efficiency of the laser's energy. Despite these challenges, progress is being made. Researchers are already testing small-scale prototypes, and the potential benefits are too significant to ignore. Laser propulsion could not only transform how we explore our solar system, but also pave the way for humanity's first steps into interstellar space. As we continue to push the boundaries of what's possible, laser propulsion stands out as a technology that could redefine our understanding of space travel. Next, we'll explore another fascinating concept, exoplanet exploration, and how we're developing the tools to study distant worlds beyond our solar system. Now, let's turn our attention to the stars specifically, the worlds that orbit them. Exoplanet exploration is one of the most thrilling frontiers in space science, offering us the chance to discover planets beyond our solar system that could potentially support life. Over the past few decades, advancements in technology have allowed us to detect and study these distant worlds in ways that were once unimaginable. The search for exoplanets relies heavily on powerful telescopes, both on Earth and in space. One of the most famous tools in this quest is the Kepler Space Telescope, which has identified thousands of exoplanets since its launch. Kepler works by observing the slight dimming of a star's light as a planet passes in front of it, a method known as the transit technique. This allows scientists to determine the planet's size, orbit, and even some clues about its atmosphere. More recently, the James Webb Space Telescope has taken exoplanet exploration to new heights. With its advanced infrared capabilities, Webb can analyze the atmospheres of distant planets, searching for signs of water, oxygen, methane, and other molecules that might indicate habitability. This level of detail brings us closer than ever to answering the age-old question: are we alone in the universe, but telescopes are just one piece of the puzzle? Space probes and missions are also being designed to study exoplanets up close. For example, the European Space Agency's Ariel mission, set to launch in the next decade, will focus on analyzing the atmospheres of hundreds of exoplanets, providing a wealth of data about their composition and potential to support life. Similarly, NASA's upcoming Nancy Grace Roman Space Telescope will use a technique called microlensing to detect planets that are too far away or too small to be found using other methods. The ultimate goal of exoplanet exploration is to find Earth-like worlds, planets with the right conditions for liquid water, a stable climate, and possibly even life. Discovering such a world would be a monumental achievement, reshaping our understanding of the universe and our place within it. But even if we don't find life, the data gathered from these missions will deepen our knowledge of planetary systems and how they form, offering insights into the diversity of worlds that exist beyond our solar system. As we continue to refine our technologies and launch new missions, the possibilities for exoplanet exploration are virtually limitless. Each discovery brings us one step closer to understanding whether life exists elsewhere in the cosmos, and perhaps even finding a second home for humanity. Next, we'll dive into the fascinating world of space-based manufacturing and how it could revolutionize our ability to build and sustain life beyond Earth. Now, let's shift our focus from exploring distant worlds to building the tools and technologies that will help us thrive among them. Space-based manufacturing is a game-changing concept that could revolutionize how we create and sustain life beyond Earth. Imagine a future where we don't just send everything we need into space from Earth, but instead we manufacture it right there in orbit or on other celestial bodies. This idea isn't just science fiction, it's a practical solution to some of the biggest challenges of deep space exploration. One of the most significant advantages of space-based manufacturing is the unique environment of microgravity. On Earth, gravity affects how materials behave, often limiting the quality and precision of certain products. But in space, the absence of strong gravitational forces allows for the creation of materials with properties that are impossible to achieve on our planet. For example, in microgravity, metals can be mixed more evenly, creating alloys that are stronger and more durable. Similarly, crystals grown in space are often larger and more pure, making them ideal for use in advanced electronics and medical devices. Another benefit is the potential to reduce the cost and complexity of space missions. Right now, launching materials and equipment from Earth is incredibly expensive. Every kilogram we send into space adds to the cost, and there's always the risk of damage during launch. But if we can manufacture tools, spare parts, and even habitats in space, we can drastically cut down on the amount of cargo we need to transport. This not only saves money, but also makes missions more sustainable and efficient. Space-based manufacturing could also play a crucial role in supporting long-term human presence in space. Imagine a scenario where astronauts on Mars need a replacement part for their habitat or a new tool for an experiment. Instead of waiting months for a resupply mission from Earth, they could simply manufacture what they need on site using 3D printers and locally sourced materials. This level of self-sufficiency is essential for deep space missions, where resupply from Earth isn't always feasible. One exciting example of this technology in action is the use of 3D printing in space. NASA and other space agencies have already tested 3D printers on the International Space Station, successfully creating tools and components in microgravity. These experiments have proven that it's possible to manufacture high-quality items in space, paving the way for more advanced applications in the future. Companies are also exploring the idea of using lunar or Martian soil, known as regolith, as raw material for 3D printing, which could enable the construction of habitats and infrastructure directly on these worlds. Beyond practical applications, space-based manufacturing could also open up entirely new industries. Imagine factories in orbit producing advanced materials, pharmaceuticals, or even art that can only be made in microgravity. These products could be shipped back to Earth, creating a new economic sector that benefits both space exploration and life on our home planet. As we look to the future, space-based manufacturing represents a critical step toward making deep space exploration not just possible but sustainable. By harnessing the unique conditions of space, we can build the tools, habitats, and technologies needed to support human life far beyond Earth. Next, we'll explore how plasma propulsion could take us even farther into the cosmos, offering a faster and more efficient way to travel between planets and beyond. Now, let's take a leap into the future of space travel with a concept that could redefine how we explore the cosmos: plasma propulsion. Unlike traditional chemical rockets, which rely on burning fuel to generate thrust, plasma propulsion harnesses the power of ionized gas plasma to propel spacecraft at incredible speeds. This technology isn't just about going faster, it's about going farther, more efficiently, and with less fuel. At its core, plasma propulsion works by accelerating charged particles, or ions, using electric or magnetic fields. These ions are expelled from the spacecraft at extremely high velocities, creating thrust. Because plasma propulsion systems can achieve much higher exhaust velocities than chemical rockets, they require significantly less fuel to achieve the same amount of thrust. This makes them ideal for long-duration missions, where carrying large amounts of fuel would be impractical. One of the most exciting aspects of plasma propulsion is its efficiency. Traditional rockets are limited by the amount of fuel they can carry, which restricts how far they can go. But with plasma propulsion, spacecraft can travel much greater distances using the same amount of fuel. For example, a mission to Mars using plasma propulsion could take less time and require less fuel than one using chemical rockets. This efficiency opens up new possibilities for exploring the outer planets, asteroids, and even interstellar space. Plasma propulsion also has the potential to make interplanetary travel more sustainable. By reducing the amount of fuel needed, we can decrease the cost and environmental impact of space missions. This is especially important as we look toward establishing a permanent human presence on other planets. Imagine a future where spacecraft powered by plasma propulsion regularly ferry supplies and personnel between Earth and Mars, making interplanetary travel as routine as air travel is today. One of the most well-known examples of plasma propulsion in action is NASA's Dawn mission, which used ion thrusters to explore the asteroid Vesta and the dwarf planet Ceres. These thrusters allowed Dawn to travel farther and longer than any previous mission, demonstrating the potential of plasma propulsion for deep space exploration. Similarly, private companies and space agencies are now developing advanced plasma propulsion systems that could one day take us to the outer reaches of the solar system and beyond. But plasma propulsion isn't without its challenges. While it's highly efficient, it generates relatively low thrust compared to chemical rockets. This means it's better suited for long-duration missions where speed can build up over time rather than quick bursts of acceleration. Additionally, the technology requires a reliable power source such as solar panels or nuclear reactors to generate the electricity needed to create and accelerate plasma. Overcoming these challenges will be key to unlocking the full potential of this revolutionary technology. As we look ahead, plasma propulsion represents a critical step toward making interplanetary travel faster, more efficient, and more sustainable. By harnessing the power of ionized gas, we can push the boundaries of what's possible in space exploration, opening up new frontiers for discovery and adventure. Next, we'll dive into the challenges of space debris and the innovative technologies being developed to keep our cosmic highways clear for future missions. Now, let's shift our focus to a pressing issue that could shape the future of space exploration: space debris removal. As humanity continues to venture into the cosmos, the growing amount of debris orbiting Earth has become a significant challenge. From defunct satellites to spent rocket stages, this clutter poses a serious risk to both current and future missions. But innovative technologies are emerging to tackle this problem, ensuring that our cosmic highways remain clear and safe. Space debris, often referred to as space junk, consists of millions of objects orbiting Earth at incredibly high speeds. Even small pieces of debris can cause catastrophic damage to spacecraft, satellites, and even the International Space Station. The danger lies in the fact that collisions can create even more debris, leading to a cascading effect known as the Kessler syndrome. If left unchecked, this could render certain orbits unusable, severely limiting our ability to explore and utilize space. To address this issue, scientists and engineers are developing a range of technologies designed to remove or mitigate space debris. One promising approach involves using robotic arms or nets to capture and deorbit larger pieces of debris. These systems can be mounted on specialized spacecraft, which then guide the debris back into Earth's atmosphere, where it burns up harmlessly. Another method involves using lasers to nudge smaller debris out of orbit, reducing the risk of collisions. One of the most ambitious projects in this field is the European Space Agency's Clear Space 1 mission. Scheduled for launch in the near future, this mission aims to capture and remove a large piece of debris using a robotic arm. If successful, it could pave the way for more large-scale debris removal efforts, helping to clean up Earth's orbit and make space safer for future missions. Another innovative solution involves designing satellites and spacecraft with built-in mechanisms to deorbit themselves at the end of their operational lives. These systems, known as end-of-life disposal technologies, ensure that satellites don't become part of the debris problem. For example, some satellites are equipped with drag sails that deploy once their mission is complete, slowing them down and causing them to re-enter Earth's atmosphere. Private companies are also stepping up to tackle the space debris challenge. Startups are developing advanced tracking systems to monitor debris in real time, providing valuable data to help spacecraft avoid collisions. Others are exploring the use of harpoons, tethers, and even magnetic fields to capture and remove debris. These efforts highlight the growing collaboration between governments, space agencies, and private industry to address this critical issue. While the challenge of space debris is immense, the technologies being developed offer hope for a cleaner, safer space environment. By removing debris and preventing its accumulation, we can ensure that future missions, whether to the Moon, Mars, or beyond, can proceed without unnecessary risk. This is not just about protecting our current infrastructure, it's about preserving the possibilities of space exploration for generations to come. As we look to the future, the removal of space debris represents a vital step in ensuring the sustainability of our activities in space. With continued innovation and collaboration, we can turn the tide on this growing problem, making space safer and more accessible for all. Next, we'll explore how bioengineered life support systems could revolutionize long-duration space missions, offering new ways to sustain human life in the harshest environments. Now, let's turn our attention to a concept that could redefine how humans survive in the vastness of space: bioengineered life support systems. As we venture further into the cosmos, the challenge of sustaining human life for extended periods becomes increasingly critical. Traditional life support systems, while effective, are bulky, resource-intensive, and limited in their ability to adapt to the unpredictable environments of deep space. Enter bioengineered organisms, tiny, living machines designed to provide oxygen, recycle waste, and even produce food, all while thriving in the harsh conditions of space. Bioengineered life support systems harness the power of biology to create self-sustaining ecosystems. Imagine a spacecraft equipped with algae that not only produce oxygen through photosynthesis, but also convert carbon dioxide exhaled by astronauts into usable resources. These organisms can be genetically modified to maximize efficiency, ensuring they function optimally in microgravity or low-light conditions. This approach not only reduces the need for heavy mechanical systems, but also creates a more natural and sustainable environment for astronauts. One of the most promising applications of bioengineered life support is in waste recycling. On Earth, nature has perfected the art of breaking down waste into nutrients that fuel new life. In space, bioengineered microbes can replicate this process, turning human waste into clean water, nutrients for plants, and even biofuel. This closed-loop system minimizes the need for resupply missions, making long-duration missions to Mars or beyond more feasible. Another exciting development is the use of bioengineered plants to grow food in space. Scientists are working on creating crops that can thrive in the unique conditions of space habitats, such as low gravity and limited sunlight. These plants could provide fresh, nutritious food for astronauts, while also contributing to the overall life support system by producing oxygen and absorbing carbon dioxide. Imagine a future where astronauts tend to gardens of bioengineered crops, creating a self-sustaining oasis millions of miles from Earth. Bioengineered life support systems also offer psychological benefits. Living in a sterile, mechanical environment for months or even years can take a toll on mental health. Introducing living organisms into space habitats can create a more comforting and familiar atmosphere, helping astronauts feel more connected to Earth. The presence of plants and other life forms can reduce stress and improve overall well-being, which is crucial for the success of long-duration missions. Of course, developing these systems is not without its challenges. Bioengineered organisms must be carefully designed to withstand the rigors of space, including radiation, temperature fluctuations, and limited resources. There's also the risk of unintended consequences, such as mutations or disruptions to the ecosystem. However, with advancements in genetic engineering and biotechnology, these hurdles are becoming increasingly surmountable. As we look to the future, bioengineered life support systems represent a groundbreaking shift in how we approach space exploration. By integrating biology with technology, we can create environments that not only sustain life but also enhance it, paving the way for humanity's journey to the stars. Next, we'll dive into the fascinating world of hyperspectral imaging and how it could unlock the secrets of distant planets and moons. Now, let's shift our focus to a technology that could revolutionize how we study distant worlds: hyperspectral imaging. This advanced technique allows scientists to analyze the composition of planets and moons in unprecedented detail, opening up new possibilities for discovering signs of life or valuable resources. Unlike traditional imaging, which captures only visible light, hyperspectral imaging collects data across hundreds of narrow spectral bands, revealing information that would otherwise remain hidden. Hyperspectral imaging works by detecting the unique spectral signatures of different materials. Every substance reflects, absorbs, and emits light in distinct ways, creating a kind of fingerprint that can be identified through this technology. For example, minerals like hematite or olivine have specific spectral signatures, as do organic compounds that might indicate the presence of life. By analyzing these signatures, scientists can map the surface composition of distant planets and moons, identifying areas rich in resources or potential habitats for life. One of the most exciting applications of hyperspectral imaging is in the search for extraterrestrial life. On Earth, this technology has been used to detect microbial life in extreme environments such as hot springs or deep sea vents. By applying the same principles to other planets, we could identify biosignatures, chemical or physical markers that suggest the presence of life. For instance, if a planet's atmosphere contains methane and oxygen in specific ratios, it could indicate biological activity. Hyperspectral imaging could also detect pigments like chlorophyll, which are associated with photosynthesis even on distant worlds. Beyond the search for life, hyperspectral imaging is a powerful tool for resource exploration. Imagine a future where spacecraft equipped with hyperspectral sensors scan asteroids or moons for valuable minerals like platinum, gold, or rare earth elements. These resources could be used to support deep space missions or even brought back to Earth, reducing our reliance on terrestrial mining. By identifying resource-rich areas, we can prioritize exploration targets and make space missions more efficient and cost-effective. Another advantage of hyperspectral imaging is its ability to study planetary atmospheres. By analyzing the light passing through a planet's atmosphere, scientists can determine its composition, temperature, and even weather patterns. This information is crucial for understanding whether a planet could support human life or if it has the potential for terraforming. For example, detecting water vapor or carbon dioxide in an exoplanet's atmosphere could suggest the presence of liquid water or a greenhouse effect, both of which are key to habitability. Of course, hyperspectral imaging is not without its challenges. The technology requires highly sensitive instruments and vast amounts of data, which can be difficult to manage and analyze. Additionally, interpreting spectral signatures from distant worlds requires a deep understanding of planetary geology and chemistry. However, advancements in artificial intelligence and machine learning are making it easier to process and interpret this data, bringing us closer to unlocking the secrets of the cosmos. As we continue to explore the universe, hyperspectral imaging will play a crucial role in our quest to understand distant planets and moons. By revealing the hidden details of these worlds, this technology could help us find signs of life, discover valuable resources, and even determine the best candidates for future human colonization. Next, we'll explore the next generation of space telescopes and how they're set to transform our understanding of the universe. Now, let's turn our gaze upward to the stars and explore the next frontier in our quest to understand the cosmos, space-based telescopes. These incredible instruments are set to revolutionize our understanding of the universe, offering unprecedented clarity and insight into the mysteries of deep space. Unlike ground-based telescopes, which are limited by Earth's atmosphere, space-based telescopes operate in the vacuum of space, free from atmospheric distortion. This allows them to capture images and data with extraordinary precision, revealing details that were once beyond our reach. One of the most groundbreaking examples of this technology is the James Webb Space Telescope, often referred to as the successor to the Hubble Space Telescope. Launched in December 2021, the James Webb Telescope is designed to observe the universe in infrared light, allowing it to peer through cosmic dust and study the earliest galaxies that formed after the Big Bang. Its advanced instruments can detect the faintest signals from stars and planets billions of light years away, providing a window into the universe's infancy. By studying these ancient galaxies, scientists hope to uncover clues about how the universe evolved and how the first stars and planets came into existence. But the James Webb Telescope is just the beginning. The next generation of space-based telescopes promises even more remarkable capabilities. For instance, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will focus on dark energy and exoplanets. With its wide-field instrument, it will map the distribution of galaxies across vast regions of the universe, helping scientists understand the mysterious force driving the universe's accelerated expansion. At the same time, it will search for Earth-like planets in the habitable zones of distant stars, bringing us closer to answering the age-old question, are we alone in the universe? Another exciting development is the concept of interferometry, where multiple space-based telescopes work together as a single, massive observatory. By combining the light collected by several telescopes, this technique can achieve resolutions far beyond what a single telescope could accomplish. Imagine being able to see the surface of an exoplanet or the intricate details of a black hole's event horizon. Projects like the Laser Interferometer Space Antenna, or LISA, aim to detect gravitational waves from space, offering a new way to observe cosmic events like the collision of black holes or the birth of neutron stars. Space-based telescopes also play a crucial role in studying our own solar system. Instruments like the Hubble Space Telescope have provided stunning images of planets, moons, and asteroids, revealing details about their atmospheres, surfaces, and potential for life. Future telescopes could take this even further, mapping the composition of distant moons like Europa or Enceladus, which are believed to harbor subsurface oceans. By analyzing the light reflected from these bodies, scientists can search for signs of water, organic molecules, or even microbial life. Of course, building and launching space-based telescopes is no small feat. These instruments require cutting-edge technology, precise engineering, and significant investment. They must withstand the harsh conditions of space, including extreme temperatures and radiation, while maintaining their delicate alignment and calibration. Yet, the rewards far outweigh the challenges. Each new telescope brings us closer to answering fundamental questions about the universe, from the nature of dark matter and dark energy to the origins of life itself. As we look to the future, space-based telescopes will continue to push the boundaries of human knowledge. They will not only deepen our understanding of the cosmos, but also inspire new generations of scientists, engineers, and dreamers. With every new discovery, we take another step toward unraveling the mysteries of the universe and our place within it. Next, we'll delve into the fascinating world of autonomous spacecraft and how they're transforming the way we explore the final frontier. Now, let's shift our focus to a technology that's redefining how we explore the cosmos: autonomous spacecraft. These advanced machines are designed to operate independently, making critical decisions without human intervention, and they're playing an increasingly vital role in deep space exploration. Imagine a spacecraft that can navigate the vastness of space, analyze its surroundings, and adapt to unexpected challenges, all on its own. This isn't science fiction. It's the reality of autonomous spacecraft, and it's transforming the way we approach missions beyond Earth. One of the key advantages of autonomous spacecraft is their ability to handle the immense distances and communication delays involved in deep space exploration. When a spacecraft is millions or even billions of miles away, sending commands from Earth can take minutes, hours, or even days to reach it. By the time a response is received, the situation on board may have already changed. Autonomous systems solve this problem by allowing spacecraft to process data, make decisions, and execute actions in real time. For example, NASA's Perseverance rover on Mars uses autonomous navigation to avoid obstacles and choose the safest path across the Martian terrain, ensuring it can continue its mission without constant input from Earth. But autonomy goes beyond navigation. Autonomous spacecraft are equipped with sophisticated artificial intelligence systems that can analyze scientific data, prioritize tasks, and even troubleshoot technical issues. Take the European Space Agency's Rosetta mission, which successfully landed a probe on a comet. The spacecraft had to autonomously adjust its trajectory and landing strategy based on real-time data, as human intervention wasn't feasible due to the distance. This level of autonomy is crucial for missions to distant planets, moons, and asteroids, where human oversight is limited. Another exciting application of autonomous spacecraft is in the search for extraterrestrial life. Future missions to icy moons like Europa or Enceladus will rely on autonomous systems to drill through ice, analyze samples, and detect signs of microbial life. These spacecraft will need to make split-second decisions about where to explore and what data to collect, maximizing the scientific return of the mission. By combining advanced sensors, machine learning algorithms, and decision-making software, autonomous spacecraft can act as tireless explorers, uncovering secrets that would otherwise remain hidden. Of course, developing autonomous spacecraft isn't without its challenges. Creating systems that can operate reliably in the harsh conditions of space requires cutting-edge technology and rigorous testing. Engineers must ensure that these spacecraft can handle unexpected scenarios, from equipment malfunctions to sudden changes in their environment, but the potential rewards are immense. Autonomous spacecraft can extend the reach of human exploration, enabling missions to destinations that are too distant, dangerous, or complex for traditional approaches. As we look to the future, autonomous spacecraft will play a central role in our quest to explore the universe. They'll allow us to venture deeper into space, gather more data, and make discoveries that were once thought impossible. From mapping distant planets to searching for signs of life, these intelligent machines are opening new frontiers in our understanding of the cosmos. Next, we'll explore how space-based internet systems are revolutionizing global connectivity and supporting deep space missions. Now, let's turn our attention to a concept that's not only transforming life on Earth but also enabling deeper exploration of space: space-based internet. Imagine a world where high-speed internet is accessible everywhere, from remote villages to the farthest reaches of our solar system. This is the promise of space-based internet systems, and they're poised to revolutionize how we stay connected, both on our planet and beyond. At its core, space-based internet relies on a network of satellites orbiting Earth, working together to provide seamless global coverage. Companies like SpaceX with their Starlink project are already deploying thousands of small satellites to create this interconnected web. These satellites communicate with ground stations and user terminals, delivering internet access to even the most isolated regions. But the implications go far beyond just connecting rural areas or improving streaming speeds. Space-based internet could be a game changer for deep space missions, enabling real-time communication between Earth and spacecraft exploring distant worlds. One of the biggest challenges in deep space exploration is the delay in communication caused by vast distances. Traditional methods rely on ground-based antennas, which can only maintain contact with spacecraft when they're within line of sight. Space-based internet systems, however, could act as a relay network, ensuring continuous communication no matter where a spacecraft is in the solar system. This would allow mission controllers to receive data and send commands without the frustrating delays we currently face. For example, a rover on Mars could transmit high-resolution images and scientific data almost instantly, rather than waiting hours or even days for the information to reach Earth. But the benefits don't stop there. Space-based internet could also support the growing number of satellites and spacecraft in orbit around Earth. With more missions launching every year, the demand for reliable communication links is skyrocketing. A robust space-based internet network could streamline data transfer between satellites, reducing congestion and improving efficiency. This would be especially valuable for missions that require real-time coordination, such as Earth observation or disaster response. Looking further ahead, space-based internet could play a crucial role in establishing a sustainable presence on the Moon and Mars. Future lunar bases or Martian colonies will need reliable communication links to stay connected with Earth and with each other. A space-based internet network could provide the backbone for this interplanetary communication, enabling everything from video calls to data sharing. It could even support autonomous systems, allowing robots and rovers to collaborate and share information in real time. Of course, building such a network comes with its own set of challenges. Launching and maintaining thousands of satellites requires significant resources, and there are concerns about space debris and orbital congestion. Engineers are also working to ensure these systems can withstand the harsh conditions of space, from extreme temperatures to radiation. But the potential rewards are immense. Space-based internet could bridge the digital divide on Earth, empower deep space exploration, and pave the way for humanity's expansion into the cosmos. As we continue to push the boundaries of what's possible, space-based internet stands as a testament to human ingenuity. It's not just about faster downloads or better streaming. It's about connecting humanity in ways we've never imagined. From enabling global communication to supporting missions to distant worlds, this technology is shaping the future of exploration. Next, we'll dive into how nanotechnology is unlocking new possibilities for space travel and beyond. Now, let's shift our focus to a groundbreaking field that's redefining the possibilities of space exploration: nanotechnology. Picture this: tiny machines, smaller than a grain of sand, working together to build stronger materials, detect microscopic changes, or even repair damaged spacecraft. This isn't science fiction, it's the reality of nanotechnology, and it's set to revolutionize how we explore the cosmos. At its heart, nanotechnology involves manipulating matter at the atomic and molecular scale. In space, this technology could lead to the creation of advanced materials that are lighter, stronger, and more durable than anything we have today. Imagine spacecraft hulls that can self-repair after being struck by micrometeoroids, or solar panels that are ultra-thin yet incredibly efficient. These innovations could drastically reduce the weight and cost of missions while increasing their longevity and reliability. But the potential of nanotechnology doesn't stop at materials. Tiny sensors built using nanoscale components could revolutionize how we monitor spacecraft and their environments. These sensors could detect everything from radiation levels to the presence of water or organic molecules on distant planets. For example, a rover equipped with nanosensors could analyze the soil of Mars in real time, providing instant data about its composition and potential habitability. This would not only speed up scientific discoveries but also reduce the need for bulky, power-hungry equipment. Nanotechnology could also play a critical role in keeping astronauts healthy during long-duration missions. Medical devices at the nanoscale could monitor vital signs, deliver targeted treatments, or even repair damaged tissues at the cellular level. Imagine a tiny device that could detect and neutralize harmful bacteria in a spacecraft's water supply, or a nanobot that could repair a fractured bone in zero gravity. These advancements could make deep space travel safer and more sustainable, ensuring that astronauts remain healthy even on missions lasting years. One of the most exciting applications of nanotechnology is in propulsion systems. Researchers are exploring how nanomaterials could be used to create more efficient fuel cells or even entirely new methods of propulsion. For instance, nano-sized particles could be used to enhance the performance of ion drives, making them more powerful and energy efficient. This could enable faster travel to distant destinations, opening up new possibilities for exploration. Of course, developing nanotechnology for space comes with its own set of challenges. Working at such a small scale requires precision engineering and rigorous testing to ensure reliability in the harsh conditions of space. There are also concerns about the long-term effects of nanomaterials on human health and the environment. But as research progresses, these hurdles are being overcome, bringing us closer to a future where nanotechnology is an integral part of space exploration. As we look to the stars, nanotechnology offers a glimpse of what's possible when we think small to achieve big things. From stronger materials to smarter sensors and advanced medical devices, this technology is poised to transform every aspect of space travel. It's a reminder that sometimes the smallest innovations can have the biggest impact. Next, we'll explore the concept of interstellar arcs and how they could carry humanity to distant star systems over generations. Now let's venture into a concept that feels like it's straight out of a science fiction epic, but could one day become a reality: interstellar arcs. Imagine a massive, self-sustaining spacecraft designed to carry not just a handful of astronauts, but entire communities of people, traveling across the vast emptiness of space to reach distant star systems. These interstellar arcs would be more than just ships. They'd be entire ecosystems capable of supporting human life for generations. The idea behind interstellar arcs is to create a spacecraft that can sustain a population over the incredibly long timescales required to travel between stars. Unlike missions to Mars or the Moon, which take months or years, interstellar journeys could take centuries or even millennia. This means the arc would need to function as a closed-loop system, recycling air, water, and nutrients to keep its inhabitants alive and healthy. Think of it as a miniature Earth, complete with farms, water purification systems, and even artificial gravity to simulate the conditions of home. One of the biggest challenges in designing an interstellar arc is ensuring the survival and well-being of its passengers over such long periods. This isn't just about physical health, it's also about maintaining social structures, mental health, and cultural continuity. Imagine being born on a ship, living your entire life there, and knowing that your descendants might be the ones to finally reach the destination. To make this work, the ark would need to be more than a machine. It would need to be a home, a community, and a society all in one. Another critical aspect of interstellar arcs is propulsion. Traditional rocket engines simply aren't efficient enough for such long journeys. Instead, these arcs might rely on advanced propulsion systems like nuclear fusion or even solar sails to gradually build up speed over time. Some designs even propose using the gravity of stars or planets to slingshot the arc toward its destination. The key is to find a balance between speed and sustainability, ensuring the arc can travel far enough without running out of resources. Of course, building an interstellar arc would require overcoming immense technological and logistical challenges. We'd need to develop materials that can withstand the rigors of space for centuries, create reliable life support systems that never fail, and design habitats that can adapt to the changing needs of their inhabitants. There's also the question of who would go on such a journey and how they would govern themselves. Would it be a small, carefully selected group, or a diverse community representing all of humanity? These are questions that go beyond science and touch on ethics, philosophy, and the very nature of what it means to be human. Despite the challenges, the concept of interstellar arcs offers a tantalizing vision of humanity's future. It's a reminder that our species has always been driven by curiosity and the desire to explore the unknown. While the idea of traveling to another star system may seem distant, it's a goal that could one day unite us as we work together to reach for the stars. Next, we'll explore the fascinating and mysterious idea of dark matter propulsion and how it could potentially unlock the secrets of interstellar travel. Now, let's shift our gaze to one of the most enigmatic and intriguing concepts in deep space exploration: dark matter propulsion. Dark matter, the mysterious substance that makes up about 27% of the universe, has long puzzled scientists. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. But what if we could harness this elusive material to power our journey to the stars? The idea of using dark matter as a propulsion source is still in the realm of theory, but it's a concept that could revolutionize interstellar travel. Imagine a spacecraft that doesn't rely on traditional fuels or even nuclear energy, but instead taps into the gravitational potential of dark matter. Since dark matter interacts primarily through gravity, a propulsion system could theoretically use its immense gravitational pull to generate thrust. This would allow a spacecraft to accelerate continuously without the need for massive fuel reserves, potentially reaching speeds that could make interstellar travel feasible within a human lifetime. One of the most exciting aspects of dark matter propulsion is its potential efficiency. Unlike conventional propulsion systems, which require enormous amounts of fuel to achieve high speeds, a dark matter drive could operate almost indefinitely, as long as it remains within regions rich in dark matter. This could drastically reduce the mass of a spacecraft, making it lighter, faster, and more capable of reaching distant star systems. Some theories even suggest that dark matter could be used to create a form of warp drive, bending spacetime itself to allow for faster-than-light travel. However, the challenges of developing dark matter propulsion are immense. For starters, we still don't fully understand what dark matter is or how it behaves. While we know it exists due to its gravitational effects on galaxies and galaxy clusters, we've yet to directly detect or study it. This means that any propulsion system based on dark matter would require groundbreaking advancements in both physics and engineering. We'd need to develop technologies capable of interacting with dark matter in ways we can't yet imagine, as well as methods to harness its energy safely and efficiently. Another hurdle is the distribution of dark matter in the universe. While it's abundant on cosmic scales, it's also spread out thinly, meaning a spacecraft would need to travel through vast regions of space to collect enough dark matter to generate meaningful propulsion. This raises questions about the practicality of such a system and whether it could ever be scaled down to a size suitable for human spaceflight. Despite these challenges, the concept of dark matter propulsion represents a bold and visionary approach to interstellar travel. It pushes the boundaries of our understanding of physics and challenges us to think beyond the limits of current technology. While it may be decades or even centuries before we see a dark matter-powered spacecraft, the idea itself inspires us to dream bigger and explore the unknown. As we wrap up our journey through these 30 groundbreaking concepts in deep space exploration, it's clear that the future of space travel is filled with possibilities. From light sails to interstellar arcs, and now to the tantalizing potential of dark matter propulsion, each idea offers a glimpse into a future where humanity reaches beyond the confines of our solar system. Which of these concepts excites you the most? Let us know in the comments below, and don't forget to like, subscribe, and hit the notification bell to stay updated on the latest in futuristic technologies and space exploration. The stars are waiting, and the journey is just beginning. As we bring our exploration of these 30 groundbreaking concepts to a close, it's impossible not to feel a sense of awe at the sheer ingenuity and ambition behind each idea. From the elegance of LightSail propulsion to the audacity of dark matter drives, these technologies represent humanity's relentless drive to push the boundaries of what's possible. Each concept, whether rooted in current science or speculative theory, offers a unique pathway to the stars, challenging us to rethink how we explore the cosmos and what it means to be a spacefaring civilization. These ideas aren't just about reaching new worlds, they're about transforming how we live, travel, and even think about our place in the universe. Imagine a future where space elevators make orbital travel as routine as catching a flight, or where self-replicating robots build habitats on distant planets long before humans arrive. Picture interstellar arcs carrying generations of explorers to new star systems, or quantum communication networks linking Earth to colonies light years away. These aren't just dreams, they're possibilities waiting to be unlocked by the next wave of innovators and explorers. What's truly remarkable is how these concepts complement one another. Light sails and ion drives could propel us to nearby stars, while nuclear thermal rockets and plasma propulsion might revolutionize travel within our solar system. Orbital habitats and artificial gravity systems could make long-term space living sustainable, while asteroid mining and space-based manufacturing could provide the resources needed to fuel these endeavors. Together, they form a mosaic of technologies that could redefine humanity's future in ways we can only begin to imagine. But the journey doesn't end here. Each of these concepts raises new questions, challenges, and opportunities for discovery. How do we overcome the technical hurdles of warp drives or terraforming? What ethical considerations come with cryogenic sleep or interstellar arcs? And how do we ensure that the benefits of space exploration are shared by all of humanity? These are questions that will shape the next chapter of our cosmic story. As we look to the stars, it's clear that the future of space exploration is as vast and full of potential as the universe itself. Which of these 30 concepts excites you the most? Is it the promise of faster-than-light travel, the idea of building cities in space, or the possibility of discovering life on distant exoplanets? Let us know in the comments below. We'd love to hear your thoughts and spark a conversation about the future of space exploration. If you've enjoyed this journey through the cutting-edge technologies that could take us to the stars, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. The universe is calling, and together we can answer that call. Thank you for joining us on this adventure, and remember, the stars are not the limit. They are just